Last week we talked about propositional logic, which is the study of inferences that are valid because of the truth-functional connectives that they use. This week we're going to be talking about a different kind of logic called categorical logic, which is also the study of inferences that are valid, but they're not valid because of the truth-functional connectives that they use. They're valid because of something else that I'd like to describe now. In order to describe what makes these inferences valid, I'd like you to consider some examples. So first, consider the inference. All squares are rectangles. All rectangles have parallel sides. Therefore, all squares have parallel sides. That inference is obviously valid. There's no possible way for the premises to be true if the conclusion is false. But notice that even if we replace squares with another category, like let's say squirrels, we replace rectangles with another category, like let's say mammals, and we replace the category of having parallel sides with another category, like let's say animals, we still end up with a valid inference. Let's try that. All squirrels are mammals, all mammals are animals, therefore, all squirrels are animals. Still valid. So, both of these inferences are valid. And they're valid because of some common feature that they share. But what is that common feature? Is it a truth-functional connective that they both use? Well, no, because neither inference uses any truth-functional connective. In fact, neither inference uses any propositional connective. So it can't be because of some truth-functional connective that they use that the inferences are valid. It must be for some other reason that the inferences are valid. And in the study of categorical logic that we'll be doing this week, we'll try to understand what that other reason is. Let me say something first about the notation that we're going to use. Last week, when we did propositional logic, we used lowercase letters like P and Q to represent propositions that were being connected by some truth-functional connective. This week, in categorical logic, we're going to use uppercase letters from a different part of the alphabet. We'll use uppercase F, uppercase G, and uppercase H to represent categories that are being connected together into a single proposition. Now notice, both of the inferences that we just discussed have this form in common. The first premise says, all of the things that fall into one category, F, also fall into a second category, G. For instance, all things that fall into the category square also fall into the category rectangle. Or, all things that fall into the category squirrel also fall into the category mammal. The second premise said that all things that fall into that second category over here also fall into a third category. So, for instance, all things that fall into the category rectangle also fall into the category having parallel sides. Or, all things that fall into the category mammal also fall into the category animal. And then the conclusion said that all things that fall into that first category also fall into the third category. For instance, all things that fall into the category square fall into the category having parallel sides. Or all things that fall into the category squirrel also fall into the category animal. We can use a certain kind of diagram called a Venn diagram, after its inventor, John Venn, to represent the relationships that these premises and this conclusion describe. And using Venn diagrams, we can show that this inference, any particular example of this inference, is valid. Here's how. Remember, the first premise says all things that fall into a first category also fall into a second category. So what we do with a Venn diagram is we use a circle to represent the first category. So all the things that fall into that first category are inside this circle, and all the things that fall outside that first category are outside the circle. So this first category we've called F, and it's represented by that circle. Now if everything in that first category is also in the second category, then if we use a circle to represent the second category, the circle that we use to represent the second category has to be at least as large as the circle we use to represent the first category, because it has to include everything in the circle that we use to represent the first category. So we could draw a second circle to represent the second category, G. So if F is the category of being a square, then this interior circle represents all of the squares. If F is the category of being a squirrel, then the interior circle represents all of the squirrels. If G is the category of being a rectangle, then this exterior circle represents all the things that are rectangles. If G is the category of being a mammal, then the exterior circle represents all the things that are mammals. So the first premise tells us that all the things in the first category, all of the F's, are also G's. They're also in the second category. But the second premise tells us that all the things that are in that second category, all the things that are G's, also fall into a third category. They're H's. So we'll represent the category of H's using a circle that includes inside it everything that the G circle includes inside it, like this. So the second premise says all the things that are in the category of G are also in the category of H. We can represent that in a Venn diagram by having the circle of all the G's be inside the circle of all the H's. So if the category of G is the category of rectangles and the category of H is the category of things that have parallel lines, then the second premise says that all the things that are rectangles also have parallel lines. If the category of G is the category of mammal and the category of H is the category of animal, then the second premise tells us that all the mammals are also in the category of animals. So these three circles right here represent the information contained in premise 1 and premise 2 together. The information contained in premise 1 is represented by having the F circle inside the G circle, and the information contained in premise 2 is represented by having the G circle inside the H circle. So having these three circles concentrically arranged as they are right now represents the information contained in these two premises. But notice something. If we put the F circle inside the G circle, and we put the G circle inside the H circle, then the F circle is going to have to be inside the H circle. And if the F circle is inside the H circle, what does that represent? That represents the fact that everything that is in the F category is also in the H category. In other words, all F are H. And so, when we construct a Venn diagram to represent the information contained in these two premises, that Venn diagram will have to also represent the information contained in the conclusion. And so the Venn diagram shows us that there's no way for the premises to be true and the conclusion to be false. If the premises are both true, then the conclusion is going to have to be true. And the Venn diagram shows us that. Using Venn diagrams, there are a number of different relationships that we can visually represent between categories. I just showed you how we can represent the relationship that we're claiming to hold when we say all F or G. We're saying all the things that fall into the F category, whatever that may happen to be, also fall into the G category, whatever that may happen to be. And we represent that by putting an F circle inside a G circle to show that all the things that are F's are also G's. Here's how we would represent the claim that some F is a G. We would draw an F circle and a G circle that overlaps it, and then mark a spot that's in the intersection of the F circle and the G circle. And that shows that there is something, whatever it is, that falls into the F category, so it's an F, and it also falls into the G category, so it's also a G. So we're showing there that some F, whatever it is also a G. If we want to represent that no F is G, that nothing in the F category is in the G category, then we can draw the F circle and the G circle overlapping and shade out the area where they overlap to indicate that there is nothing in that intersection. There is nothing that is both an F and a G. And that would represent no F is G. Finally, if we want to represent the claim that some F is not G, then we could draw the F circle and draw the G circle overlapping it, but mark a spot inside the F circle but outside the G circle. That way we're showing that there is something, whatever exactly it is, that is in the F category, but it's outside the G category. So some F, whatever it is not a G. And that's how we can use Venn diagrams to represent different relationships that we could claim to hold between categories. Now, let's see how we can represent the validity of an inference that uses claims like this by means of Venn diagrams. Notice that these Venn diagrams already tell us something about the logical relations between the claims that they represent. For instance, look at the Venn diagram for some F is G. It shows us that there's a thing, don't mind what it is, but there's a thing that's in the F category and that's also in the G category. Now consider the Venn diagram for the claim no F is G. What it shows us is that there is nothing that is in the F category and in the G category. So this claim right here, no F is G, is the negation of this claim right here, some F is G. If this claim is true, if some F is G, then this claim is not true. It's not true that no F is G. And similarly, if this claim is true, no F is G, then this claim is not true. It's not true that some F is G. So this claim and this claim are negations, and you can tell that by looking at the Venn diagrams that represent them. This Venn diagram shows you that there is something in a particular area, and this Venn diagram shows you that there is nothing in that same area. But now notice, the claim some F is not G is also the negation of the claim all F are G. If all F are G, then it can't possibly be true that some F is not G. But if some F is not G, then it can't possibly be true that all F are G. So this claim and this claim are negations. And yet, the way we've done the Venn diagram for this claim, all F are G, it doesn't show that this claim is the negation of this claim. So we're going to change the Venn diagram for all F or G so that it indicates that all F or G is the negation of some F is not G. And here's how we're going to do it. We're going to draw an F circle and a G circle that overlaps it. And we're going to shade out the area of the F circle that's outside the G circle to indicate that there is nothing that is in the F circle that is not also in the G circle. Now, with this Venn diagram, you can easily see that all F or G is the negation of some F is not G. The Venn diagram for some F is not G shows you that there's a thing in the F circle that's outside the G circle, and the Venn diagram for all F or G shows you that there's nothing that's in the F circle that's outside the G circle. And so the Venn diagrams now represent the relation between some F is not G and all F are G, the same way that the Venn diagrams represent the relation between some F is G and no F is G. Venn diagrams are useful in helping us to see what the logical relationships are between different claims concerning what's true about all things of a certain kind, or some things of a certain kind, or no things of a certain kind. Let me give you an example. Consider a claim of the form all F are G, and a claim of the form no F are G. For instance, all of the sheep are in the field, and no sheep are in the field. Now, those two claims might at first sound inconsistent with each other, like they can't both be true. But if you look at the Venn diagram for all of the sheep are in the field, and the Venn diagram for no sheep are in the field, you realize, actually, that both of those claims can be true. The Venn diagram for all of the sheep are in the field shows that what that claim means is that there are no sheep that are not in the field. But it could be true that there are no sheep that are not in the field, even when it's also true that there are no sheep that are in the field. That could be true, both of those two claims can be true, whenever there are no sheep. If there are no sheep, then there are no sheep that are not in the field, and there are also no sheep that are in the field. And the Venn diagram for those two claims helps us to see that they're consistent with each other. Consider two claims of the form some F is G and some F is not G. For example, some politician is honest and some politician is dishonest. Now, at first, you might hear those two claims and think, well, wait a second. Who is this some politician that you're talking about? Whoever it is, they can't both be honest and dishonest, right? Someone can't be both honest and dishonest. So whoever this some politician that you're talking about is, one or the other of the two things that you're saying about them has got to be false. So you might think that the two claims I just made are inconsistent with each other. But again, the Venn diagram for those claims helps us to see that they're not inconsistent with each other. To say that some politician is honest is just to say that there is some politician, never mind who is honest. And again, to say that some politician is dishonest is just to say that there is some politician, never mind who's dishonest. But of course, those two claims could both be true. There could be one politician who's honest and another politician who's dishonest. So once again, the Venn diagrams for the two claims help us to see that those two claims are consistent with each other. They can both be true under certain circumstances. It'll be useful for us to label the four kinds of propositions that we've been talking about. Propositions of the form all F are G, we're going to label with the uppercase letter A. Propositions of the form no F is G, we're going to label with the uppercase letter E. Propositions of the form some f are G, we're going to label with an uppercase letter I, and propositions of the form some f is not G, we're going to label with an uppercase letter O. Using this labeling scheme, we can now describe immediate categorical inferences as inferences that have a single premise of the form A, E, I, or O. These inferences occur very commonly in everyday life, and so we're going to discuss the conditions under which they're valid.
Rom, wake up!
Oh, wow. I was just having the most boring dream. You know, some books are so boring.
Yeah, but not all books.
Oh! Not all books are boring, but does that mean that all books are not boring?